Let's say your VM0042 project has a CV of 50%. Pretty typical for a mixed agricultural landscape with varying soil types. With no stratification, you need 68 samples to hit the required 10% precision at 90% confidence. Now stratify that same project into 3 zones with average internal CVs of 25%. Suddenly you need around 28 samples total, less than half. That's real money. At $400 per composite sample, including lab, you've saved $16,000 per monitoring event. And this is a recurring saving. Every verification period. Stratification is not a statistical formality. It's a budget decision. And the wrong stratification, which is extremely common, doesn't save you anything. It just creates a problem that's expensive to fix after the fact. This video covers how to do stratification correctly, which variables to use, how to choose the number of strata, and how to run k-means clustering on your spatial data in 5 lines of Python. Stratification divides the project area into internally homogeneous zones before sampling. Each zone, each stratum, is then sampled independently. The total variance of the SOC estimate is the area-weighted average of within-stratum variances. When within-stratum variance is lower than total project variance, you need fewer samples to achieve the same precision. That's the efficiency gain. In the example from this toolkit, no stratification, CV equals 50%. You need 68 samples. 3 strata, within-stratum CV averages 25%. You need 28 samples. Same precision. 40 fewer samples. The rule is, stratify along whatever explains the most SOC spatial variation. Here's the mistake that appears in the list of top 15 rejection reasons. A lot of project developers stratify by the management activity they're implementing. Stratum 1. Farmers who adopted cover crops in year 1. Stratum 2. Farmers who adopted in year 2. This is circular reasoning. You're using the treatment to define the comparison groups. VM0042. Section 8.1 explicitly requires stratification based on pre-intervention characteristics that are independent of the project activity. The right variables are things like historical SOC estimates from satellite-derived soil maps, topographic wetness index, soil texture, long-term NDVI, things that existed before your project started, and that predict where SOC will be high and where it will be low. That's the core requirement. If stratification variables correlate with what you're doing to the land, the VVB will reject it. Let me walk through covariate selection. This is Table 5.1 from the PDF guide. I'll put a link in the description. Highest value covariates for SOC stratification, in order. First, Soil Grids SOC Estimate. ISRIC Soil Grids version 2.0, 250-meter resolution, free download. This is the satellite-derived estimate of current SOC in the top 30 centimeters. It's not perfectly accurate, but it captures the dominant spatial pattern. Second, Topographic Wetness Index, derived from a digital elevation model. High TWI means water accumulates there, drainages, depressions. Consistently higher organic matter, captures 10 to 20% of SOC variance on its own in rolling terrain. Third, clay content, also from soil grids. Clay stabilizes SOC, sandier soils lose it faster. Important for projects spanning multiple soil types. Long-term NDVI, 10-year mean from Landsat, is also useful as a proxy for historical biomass production. Keep it to 2 to 6 covariates. More than 6 rarely improves the stratification and slows the algorithm. Here's what to avoid. Current year NDVI is problematic because it's confounded by crop stage. A field photographed in early spring looks very different from the same field in August, and neither image reflects underlying soil conditions accurately. More importantly, do not use any variable that correlates with the management practice you're implementing. If cover crops improve soil conditions, and you stratify by a variable that tracks cover crop adoption, you've violated the independence requirement, and critically, All covariates must come from data measured before the project started. You cannot use post-intervention data to define strata. The VVB will ask for the date of each dataset you used. Make sure they all predate your project start. Let me build this live. The input is a data frame called units, 1 row per spatial unit, which in this case is 1 row per 30-meter pixel in the project boundary. Each row has a SOC proxy column for the soil grid's SOC estimate, a TWI column for topographic wetness index, a clay PCT column for clay percentage, and an area Chi column for the area of that pixel in hectares. For this case study, we have 200 spatial units covering 800 hectares total. The row structure doesn't have to be pixels. It could be farm parcels, field blocks, or any spatial unit you're using for your sampling frame. The key requirement is 1 row per unit, with the covariate values attached. First step, figure out how many strata to use. The function is optimal times k. You pass the data frame, the covariate columns, the range of k values to test, and the area column. The output has a column called VRR, Variance Reduction Ratio. This is the ratio of within stratum variance to total variance. Lower is better. It means the strata are capturing the SOC variation. Look at the VRR column. At k equals 2, 0.71. At k equals 3, 0.59. At k equals 4, 0.44. Then it starts flattening. 0.40, 0.38, 0.37. The recommended flag is on k equals 3. That's where the elbow is. The biggest single jump in VRR improvement. Going from 2 to 3 strata explains an additional 19 percentage points of variance. Going from 3 to 4 only adds 8 more. K equals 3 is the sweet spot for this dataset. Now run the actual stratification. The function is k-means strata. 3 parameters worth noting. Random state equals 42. Fix this and document it in your PDD. K-means has a random initialization. With a fixed seed, your results are exactly reproducible. Mean stratum fraction equals 0.02. Any stratum with less than 2% of total area gets merged into the nearest neighboring stratum. This prevents the algorithm from creating tiny slivers that are impractical to sample. The result has a new column called stratum with integer labels 0, 1, and 2, ordered by descending area. Stratum 0 is the largest at 384 hectares. Stratum 1 is 260 hectares. Stratum 2 is 156 hectares. Before you document this stratification in your PDD, you need to verify it's actually doing something useful. The stratification quality function returns 3 key statistics. VRR, 0.249. That's excellent, well below 0.40. The stratification explains about 75% of the total SOC proxy variance. F statistic, 187. P-value, effectively 0. The ANOVA F statistic and p-value tell you the strata are statistically distinct. If the strata were random groupings with no real separation, F would be near 1 and P would be near 1. A high F and low P confirms the strata actually capture different soil conditions. The interpretation string says excellent, VRR less than 0.40. This is what you want to see. If VRR is above 0.75, you might need to add a stratum, change your covariates, or accept that the landscape is simply homogeneous. The stratification summary function produces the table that goes directly into your PDD. Stratum 0, 384 hectares, area fraction 0.48, SOC proxy mean 18.4, CV 21%, recommended N 16. Stratum 1, 260 hectares, CV 35%, recommended N 26. Stratum 2, 156 hectares, CV 36%, recommended N 27. Total recommended N across all strata, 69. Compare that to 68 samples without stratification. In this particular dataset, the efficiency gain is modest because the covariates explain a lot of variance. In a more heterogeneous landscape with a less informative covariate set, the savings would be larger. The recommended DDN column is the Cochrane formula output for each stratum at 90% confidence, plus or minus 10% precision. This is what feeds into the sample size calculation in video 5. The Toolkit's reporting module generates the PDD language automatically. You pass the quality statistics, the stratum summary table, the total area, the covariate definitions, and the random seed. The output is Markdown that converts to a properly formatted PDD section. It includes the table of stratum areas, the documentation statement with all parameter values, and the mandatory language confirming independence from the project activity. This is what VM0042 Section 8.1 requires. Description of stratification variables and their sources, the algorithm used, the number of strata and rationale for K, the VRR and ANOVA statistics, and a statement confirming that no stratification variable correlates with the project activity. Here's the exact language for PDD Section 8.1. The project area was stratified into 3 strata using K-means clustering. K equals 3, random state 42, applied to soil grids SOC, topographic wetness index, and clay percentage. The variance reduction ratio is 0.249, and ANOVA confirms strata are statistically distinct. F equals 187, P less than 0.001. All stratification variables are pre-intervention and independent of the project management activity, per VM0042 Section 8.1. The Generate section or 8.1 function fills in all your actual numbers automatically. Copy the output and paste it into PDD Section 8.1. The VVB will see a properly structured documentation block with all required elements present. What if you run the quality check and VRR is above 0.75? That means your stratification isn't doing much. The strata are almost as variable as the full project. A few options. First, try different covariates. Maybe clay isn't the right variable for your landscape. Try elevation, long-term NDVI, or drainage class. Second, try more strata. Going from K equals 3 to K equals 4 might drop VRR from 0.75 to 0.55. But check that each stratum has enough area to support at least 5 to 10 samples. Third, accept it. Some landscapes are genuinely homogeneous. Flatland, single soil type, uniform management history. If VRR is 0.72 and you can't get it lower with reasonable covariates, document your attempt. Explain the landscape characteristics and use K equals 2 or even K equals 1 with a higher sample size. High VRR doesn't fail validation on its own. What fails validation is using management zones as strata or having no documented rationale for your stratification design. Here's the VRR interpretation table for reference. VRR below 0.40 is excellent. The strata explain more than 60% of total variance, and you'll see a strong efficiency gain in your sample size calculation. VRR between 0.40 and 0.75 is acceptable. There's meaningful variance reduction, and you should proceed with a documented rationale. VRR above 0.75 is poor. Your stratification adds little value, and you should try different covariates or more strata before accepting it. At all VRR levels, the ANOVA p-value must be below 0.05 to confirm the strata are statistically distinct. An insignificant ANOVA result at any VRR means the strata are not meaningfully separated and should not be used. There are 6 elements that PDD Section 8.1 requires, and the VVB will check for all of them. First, the stratification variables, names, sources, spatial resolution, and rationale for each one. Second, the algorithm. KA means clustering with a citation or reference. If you use a different algorithm, you need a justification. Third, the number of strata and the rationale for that choice. The elbow criterion on the VRR table is the standard approach. Fourth, the VRR value and ANOVA statistics, the actual numbers, not just a statement that the test passed. Fifth, the random seed you used. This is critical for reproducibility. If someone reruns your analysis with the same seed, they must get the same strata. Sixth, an explicit statement that no stratification variable correlates with the project management activity. The Generate section, Chakra 8.1 function, populates all 6 elements automatically. The full stratification workflow is 4 steps. Step 1. Select your covariates. They must be pre-intervention and independent of the project activity. Soil grids, SOC plus topographic wetness index, is a strong starting point for most agricultural projects. Step 2. Find the optimal K using optimal KO and the VRR elbow criterion. Step 3. Run KO means with KO means notch strata, with a fixed random state, and check the stratum area distribution. Step 4. Run the quality check, generate the summary table, and auto-generate the PDD language. The entire workflow, from raw spatial data to PDD-ready text, takes under an hour once you have your covariates assembled. The covariate assembly is the time-consuming part. Downloading soil grids, clipping to your project boundary, computing the topographic wetness index from a DEM. Chapter 5. Section 5.1 of the PDF guide has step-by-step instructions for each data source. 3 things to take away from this video. First, stratification variables must be pre-intervention and independent of the management activity. Soil grids, SOC, and topographic wetness index are your best starting points. Never stratify by management zone. This is the most common stratification mistake, and it causes validation rejection. Second, choose the number of strata using the VRR elbow criterion. Target VRR below 0.40. Verify with ANOVA. Fix the random state and document it in the PDD. Third, the PDD requires 6 elements in section 8.1. The generate section *8.1 function handles all of them automatically. Variable sources, algorithm, rationale, VRR, ANOVA, and the independent statement. Video 5 covers sample size calculation, the next step after stratification. Once you have your strata and their internal CVs from pilot sampling, the Cochrane formula tells you exactly how many samples each stratum needs. See you there.